Okay. Of course, in a similar manner, you can also prove that similarly, if A and B are two real numbers, A less than B, then similar to our previous proof that the minus infinity C is opened, you can show that the AB open interval is open, is an open subset in Rn. In R1, that is R, the real numbers. Therefore, the pre-image of this is also opened in Rn. Okay. For this, I will give you an interesting example. For this function, the norm fx equal to norm of x. What is the pre-image of AB interval? So for the above, for the f here, if A is positive, or maybe if B is greater than A and A is positive, then the pre-image of this open interval is the points so that the norm of x, that is fx, is greater than A but less than B. So geometrically, what this set look like? This set is obviously an angle. So this is this is a ball with radius A, and we take another ball with radius B. So our pre-image of the AB open interval is exactly this angle. Okay, so this is an open set by our discussion. Okay. Similarly, we can also obtain the closed sets. If f is a continuous function on Rn and C is a real number, and then is closed because the interval is a closed subset of R. Okay. More generally, we also have for AB in R, A less than B. This is closed. The closed interval is closed. This is why it is called closed intervals. Okay. The proof is also very easy. You want to prove that this is closed. You need to verify that any convergence sequence in this closed interval has a limit in the interval, right? So to prove that this is closed, if Tk is a sequence in the interval and Tk converges to alpha, you need to verify that alpha belongs to the interval. But Tk is a sequence in the interval implies that A is not greater than Tk, then in turn is not greater than B. And Tk converges to alpha. So by the basic property of convergent sequence of real numbers we learned long ago, we know that the limit also satisfies the same inequality. No. So this means that alpha belongs to the interval. Therefore, the interval is closed. Okay, in this section, we study the sequential compactness. This will be used to establish some useful property of continuous functions and continuous maps over bounded closed sets. To define the sequential compactness, we need to encounter a subsequence and even subsequence of subsequence. Therefore, we need some convenient notation to denote this iterative subsequence. So we introduce some notation first. Notations for taking subsequence iteratively. This means we'll take subsequence of subsequence. So, as we know, xk is a sequence. Then the subsequence usually is denoted by xki. Here, I is run from 1 to infinity. Xki is the ith term in the subsequence. Okay, but if we want to take a subsequence of xki, maybe you have to denote it by xkij and so on. So this is not very convenient. So we introduce a useful notation to deal with this. Okay, so we denote the subsequence of xk by xki1. Here, the index of the subsequence is I from 1 to infinity. Okay, and the ki1, the one here over at the place of a superscript. This means the one here means first generation. Okay, because this subsequence is the subsequence of xk. But if we, as we know, that xki1, this is itself a sequence, so we can consider its a subsequence. Okay, so the subsequence of this will be denoted by our notation. Subsequence of xki1 is denoted by xki2. Of course, the index is also still I from 1 to infinity. xki2. As you can guess, the 2 there, the 2 means the second generation. Okay. Okay, this is very clear. In general, subsequence of the alpha generation. The alpha generation will be xki alpha. Here the alpha means alpha generation. Note that the index of this subsequent, the numbering is still I from 1 to infinity. Subsequence of alpha generation will be the alpha plus 1 generation. We denote it by maybe red. xki alpha plus 1. And this complicated notation, xki alpha is the ith term of the alpha generation subsequence. Okay, to help you understand our notation, we consider an example. Suppose we have a sequence xk. The terms which even index x2, x4, x6, these terms consists an first generation subsequence. Consist xki1 first generation. So in this case, xk1 xk11 is the first term in the subsequence. Therefore, it is the second term in the original subsequence. So xk11 is x2. And xk21 is the second term in the subsequence. So this is the first term of the original subsequence. So xk21 is x4. And xk31, what's this? The third term in the subsequence, which is the sixth term in the original sequence. So xk31 is x6. Okay. Now we consider a subsequence of this first generation subsequence. We take the term from the first generation, which old index terms which old index 1, 3, 5 old. Terms which old index in the first generation subsequence consist second generation subsequence, which is denoted by xk2i. So for this second generation subsequence, the first term xk21, this is the first term in the first generation subsequence. So this will equal xk1, 1. That's x2. And the second term of the second generation subsequence, xk2, 2, which will be the third term in the first generation. So it will be xk1, 3. That's x6 in the original sequence. Okay. So I believe through this example you can understand our notation very well.